In this lecture, we are going to look at how to generate and analyze QQ plots in code, which will help us understand whether or not our daily stock returns are normally distributed. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Before we make any QQ plots, I want to start by simply drawing the normal PDF over the histogram. We know that, theoretically, the histogram will approach the true distribution as the number of samples collected approaches infinity. So if the distribution we choose is a good fit, then its histogram should match up pretty closely with the true distribution. We can start by importing the norm module from scipy.stats. Next, we can create a list of x-coordinates, which will span from the minimum return to the maximum return, with 100 points in between. As you recall, this can be accomplished with the linspace function. Next, we're going to generate the normal PDF with mean and standard deviation equal to the sample mean and sample standard deviation of our returns. We can accomplish this by calling the function norm.pdf. The first argument is the x-coordinates, the second argument is the mean, and the third argument is the scale, which for the normal distribution is the standard deviation. Next, we can draw a plot of our PDF along with the histogram simply by calling the plot function and the hist function separately. Note that for the hist function, we need to pass in the argument density equals true so that the histogram is normalized. By default, histograms show the raw counts, which of course will be much larger than the values of the PDF. So what do we see? As you can see, this is probably not quite a good fit. It's reasonable, but there are some areas of the plot which don't look nice. For example, in the center, the data has a much higher frequency than predicted by the normal distribution. There also appear to be pretty significant gaps in the shoulders of the distribution. And thirdly, the returns seem to take on pretty extreme values, which should be very unlikely according to the normal distribution. Let's now see how we can generate a QQ plot to verify what we've seen. One method of doing this is to simply use the probplot function from scipy.stats. As you recall, another name for the QQ plot is the probability plot. In the next block, we call the probplot function. The first argument is the data. That's the Starbucks returns, but we call dropNA first so that we only pass in actual numbers. Next, we say dist equals norm to say that we want to compare our data with the normal distribution. We say fit equals true so that the function will find the best parameters for the normal distribution that will match with our data. Finally, we pass in a plot equals plt, which corresponds to matplotlib, which we imported earlier. So if we look at the probability plot, what do we see? Well, we see pretty significant divergence at the ends of the probability plot. This suggests that our data has much heavier tails than expected if it came from the normal distribution, which confirms what we were seeing earlier. The next thing I want to do in this script is to show you how to make the exact same QQ plot, but using stats models rather than SciPy. Although SciPy is great at doing a few statistics calculations, stats models is much more expansive. If you come from the R language or you have a statistics background, you may have wondered if there is any analogous functionality in Python. And of course, the answer to that question is stats models. I want to introduce you to stats models now, since it will be a pretty significant staple in this course, especially when we look at time series models. So first we need to import stats models. The usual way of doing this is to say import statsmodels.api as SM, sticking with our two-letter convention for major libraries. Notice how we get this strange warning. This is not because of our code, since we haven't actually done anything. This is because of StatsModels code. Unfortunately, StatsModels is not as popular as other libraries such as NumPy or TensorFlow or PyTorch, so you're going to see things like this from time to time. If it bothers you, I would encourage you to look at the source code, figure out how to fix the issue, and then make a pull request on the StatsModels repository. Alright, so anyway, back to our QQ plot. This is as easy as simply calling sm.qqplot. As input, we pass in our data, again first calling dropNA to remove any null values, and line equals s. So what does line equals s mean? S means that the line is standardized. That is, it's scaled and shifted by the standard deviation and mean of our data. There are other possibilities such as R, which means to fit a regression line. If you want to learn about the different arguments you can pass into this function, I would encourage you to read the documentation. In any case, what do we see? Well, not surprisingly, we get a plot that looks pretty much exactly the same as what we had earlier, aside from a few minor differences, such as the axis labels. Of course, they are both QQ plots, so this must be the case. Now, as you know in finance, sometimes we like to work with the log returns rather than the returns. So let's see if anything changes when we use the log returns instead. Again, we're going to create a list of x values for the x-axis on our PDF plot. We now use the min of the log returns and the max of the log returns. Again, we have 100 points. Next, we call norm.pdf again, passing in the x values, the mean of the log returns, and the standard deviation of the log returns. We assign this to a variable called ylist. Next, we plot xlist and ylist alongside the histogram of the log returns. So what do we see? Well, we see that the picture pretty much looks exactly the same. How can this be? Well, recall that when the values of the returns are very nearly 0, adding 1 and taking the log does not change its value by a lot. In other words, x is approximately equal to log of 1 plus x when x is near 0. Again, we see the same pattern where the histogram is taller than the theoretical distribution and has much more extreme values than the theoretical distribution would admit. If we look at the QQ plot, we again see the same pattern. The points diverge at the ends because it has heavier tails compared to the theoretical distribution.